Hello everyone, this is Sanabayana Sanjeev Kumar from aerobic section. Today I am going to tell about a topic in fluid dynamics which is known as the spreading of miscible liquids. So what are miscible liquids? Coming to the topic, these miscible liquids are commonly contact one another in natural and technological situations, often in the proximity of a solid substrate. In the scenario where a drop of one liquid finds itself on a solid surface and immersed within a second, miscible liquids it will spread spontaneously across the surface. We show experimental finding of an spreading of sessile drops in a miscible environment that have distinctly different shape, evolution, and a power law dynamics from sessile drop that spread in miscible environments, which have been reported previously. As we can see, this type of liquids are contact in natural and they will not touch each other and they will be miscibles. The spreading of miscible liquids is encountered in many important natural and technological processes. In the human body, miscible liquids continuously come into contact with one another, and a prominent example is mucus interacting with other body fluids. An important technological problem in the manner in which supplied oil can spread across the bodies of animals coated with body oils. As you can see, the dissipates a spreading liquid that has formed a spherical drop in this shape is at equilibrium. This sessile drop will form a contact angle theta e given by Young's equation. Sigma LF cos theta E is equal to sigma SF minus sigma S. As this is a spreading liquid, they will spread continuously and encounters as many as natural and technological processes. As we can see, this is a schematic diagram of an miscible liquids in which it will not interact with its surface and it will spread to its extents, but it will not deform its shape. As there is a liquid A and liquid B, when we take out the take out a liquid B within a tube, as you can see that liquid A will be like a bubbles in liquid B. They will not dissolve in that, and neither they will not pop out, and they will be forming an bubble structure. Often, the spreading of liquids is studied in the context of sessile drops, as they naturally arise as either equilibrium or transitory states. When a sessile drop is in a transitory state, sessile drops in air with a finite initial contact angles, yet with equilibrium contact angles of 0, have been measured to spread with well-known power law dependencies in time. Here, the power law index depends on whether fluid flows in driven either by gravity or by capillarity, which can be determined by calculating the bond number mu of the drop. Here we can see that the spreading of liquids is natural in the process, but as we can see this miscible drops, they will not they will be in transitory state and they will make an infinite contact angles, finite contact angles, so that it will be stable for a long time. The formula given by this drop will be BO is equal to the bond number is equal to rho g r 2 sigma L F. If you scale the leading edge radius and time data presented by initial drop radius and a characteristic drainage time, respectively, the plot shown is obtained. When the horizontal axis is scaled by a characteristic drainage time, The data also largely collapsed to reveal a polar response of the time leading edge that closely follows the square root dependence in time, which is reminiscent of a diffusive process. The characteristic drainage time tau is calculated. Tau is equal to mu a by sigma s rho g HLE. As you can see, the diagrams related to this topic will be given here. As there are two types of liquids with a high sigma and a low sigma rate, that's the surface tension. As you can see, there are capillary forces acting on these two water drops when they are in contact with each other. This is also known as the viscous drag. And when they got interacted or contact within each other, the Maragoni driven encapsulation will be happened in between them, so that the final stage we get is like that, the pure material. So as you can see, the carbonated water and orange juice, as we can combine these two, we'll get a juice compound with a mixture of carbonated water and oranges, which most likely seen as a orange juice. But the liquid state will be compared to orange juice will be less. And a sessile drop immersed in a miscible environment undergoes a distinctly different shape evolution that one present in immiscible surroundings. A sessile drop spreading across a solid surface while immersed in a miscible environment develops an elevated leading edge in addition to its contact line. This elevated leading edge actually leads the radial advancement of the drop, and the contact line advances at a slower rate. Through experiments using particle imaging techniques (PTV) and confocal microscopy, fluid motion of the miscible systems was visualized. And as you can see this, the immersed in the miscible environment. And this miscible environment will tell us about the experiment with an PTV, particle imaging techniques. In this particle imaging techniques, the advanced slower rate will be calculated and will be shown with a particular time management, and also the fluid motion of this will also be shown. So thank you. This is all for the explanation about the miscible liquids. So the main theme of this thing is that the miscible liquids in the environment will also be shown the different types, and they will be dissolved. The dissolution of two liquids is also said as a miscible environment or miscible droplets. This is all about this topic. And also in this, the carbonated water, and as we can see in this case of a carbonated water and orange drink, we can say that all this will be mixed. Thank you. This is all for my explanation.